Hello, in this video I'm going to show you some experimental archaeology in ancient stoneworking. So with just copper and granite and stone, we're going to debunk the science behind the argument for advanced high-powered machines in ancient Egypt and elsewhere. I was inspired by, and I will link these videos from the Alexander Sokolov channel, how the ancient Egyptians sawed granite, and there's another demonstration where they're on the stage and they do it in real time, but I want to add some information to that as well. Using only copper and abrasive sand available at the time and described at the time, I'm going to show how a straight copper edge actually then becomes a curved copper edge, and how impossible without a giant high-speed circular saw can be achieved using nothing but primitive tools and a low-speed action. I'll also be replicating perfectly the impossible to achieve striations and grooves that can only be achieved with a high-speed, high-powered circular saw. But using nothing but copper and sand versus granite, I'm going to achieve the impossible and show that the science behind lost ancient high technology and advanced machinery is all false, because they say impossible, I'll prove otherwise. I'll also be going into the science of both modern and ancient techniques and the science behind how to work granite, both modern and ancient, and also through this particular technique that I'm using and the blade that I created. It actually forms a good way to measure the amount of copper that is lost to granite. So essentially, for every 15.4 cubic millimeters, centimeters, whatever, of granite that is grinded away with this technique, we only lose 1 in relation to that of copper. So very little copper is lost, a lot of granite gets removed. So how did I do this impossible lost high technology achievement with very simple primitive stone age, well, copper age techniques? The blade that I'm using is just a flattened piece of copper tubing. So there we have the dimensions, and most importantly the thickness of the tube itself, 1.22 millimeters. Just flattened out copper tube. So therefore the thickness of the blade is 2.44 mils, but 2.4 or 2.5. Let's not split hairs. Now I cut the slit a little bit too deep, so I just inserted some they're matchsticks from the craft shop. Those craft matchsticks, and so I just use those as spacers. It's hard to see, but again, I just inserted some wooden wedges into the side just to lock the blade in place. And the only concession I made to the modern age, I could have used wooden dowels, probably, but I used some screws just to lock the blade in place. I didn't want the blade sliding out, and I didn't want to injure my hand, so safety first. But I could have used wooden dowels. The wedges that I placed in there were actually strong enough, and that's also relevant because the action I was using, as you will see, I was holding the block at the end. I was putting very little downward force on it. It was just a backward and forward motion. I would be able to improve my rate by putting force on the blade, but that wasn't necessary. Here is the finished result. I'm going to begin the demonstration right after this, but I'll be running it at 10 times speed, so you'll see the whole process happen, but that again will be at 10 times speed. However, during that time I'll be inserting little clips, fragments, just a few very important details in regards to the process, what the actual science behind it, the history behind it, and the other records which the lost ancient high technology advanced machinery industry very actively suppresses and uses all sorts of tricky techniques to move around. Eventually I will do a video just breaking down some of these videos and the sophistry, the deception, and just the general pseudoscience which they rely upon. The abrasive I'm using is an emery grade abrasive. So I just got some crushed white quartz, crushed granite, crushed limestone, crushed sandstone, just bits and pieces that would be available to any ancient culture from their mine sites, quarry sites, etc. So my emery grade abrasive is not pure corundum. Pure corundum is 9 on the Mohs hardness scale. That was available, but I'm using an emery grade abrasive which would be 8 on the Mohs hardness scale. So also could use less, it would still work as well, but that's the abrasive that I use. Now, how did I get corundum? Corundum or aluminium oxide, also known as alumina, was available to all the ancient cultures. There are writings on this. Corundum is aluminium oxide or alumina. Most abrasive papers, grinding discs, etc. are made from aluminium oxide as the abrasive. I chose this specifically. A lot of abrasive cloths papers are made from silicon carbide, which is even harder, 9.5, but I went out of my way to get aluminium oxide abrasives to make my mix. That's just corundum. And how do you get that? Well, I'll explain that in a moment.
I just wanted to restart a marker because I can, with the blade, I can feel already there is a groove in there, which sort of means I don't actually need this guide as much now anymore. I will keep it for a while because it's still quite shallow and it's filling up with the powder, which is what I want. And then I want the blade to, push in and force against it.
The simplest way to get corundum again is to just find an abrasive paper, sandpaper, abrasive cloth, and make sure that it is aluminium oxide rather than silicon carbide. Aluminium oxide or alumina is corundum, and it's very easy to extract. You just basically burn away the cloth or the paper, and then you're left with corundum or aluminium oxide. It's harder than burning sandpaper to get your aluminium oxide, but also masonry grinding discs such as these, which just have a cloth backing. Make sure to get aluminium oxide, not silicon carbide, and that's one way to get your corundum and to make your emery mix.
Okay, I think especially because I'm getting low and soon the bottom of a wood will start rubbing on here, but I don't need that anymore. And I also want to inspect what's going on. So I'll get that water out of there. I'll try and squeeze that back in.
Plenty of great sources on corundum or aluminium oxide, but even the basics here are just covered in the Wikipedia article. Corundum is a crystalline form of aluminium oxide, aka alumina, very common, widespread throughout the world. Ancient societies that had availability to it, and we'll see they also spoke and wrote on it. Rubies and sapphires, unlike diamond, which is carbon, made from carbon, rubies and sapphires, which are very hard as well, are corundum. The word corundum is derived from Tamil Dravidian corundam, which is ruby sapphire as translated. So there's the source for it. Here are just some corundum crystals. You can find it in very large crystals, but also will be mixed with other materials, and I'll get to that in a moment. That has to do with pure corundum versus emery mixes, such as emery paper, emery cloth, which is used, but you should be familiar with that.
And now I've got my cut going, and then I can keep working with that and see where we go. Having cleaned it up, that's where we've come so far. And again, you can see, that lifts up, it's deepest in the middle, and then again goes shallow towards the end of the stroke, which is going to, as we finish, create those striation marks, which will resemble the circular saw marks in there as well. So that's so far. With these things, it takes time, but then it lasts forever once it's done, or at least as long as the granite is, and that's going to be thousands and thousands and thousands of years.
So corundum, aluminium oxide. So corundum's hardness, pure corundum, as in the crystal, is defined to be 9 on the Mohs hardness scale. It can scratch almost any other mineral. It is commonly used as abrasive on everything from sandpaper to large tools, grinding discs. Now, some emery is a mixture of corundum and other substances, and the mix is less abrasive with an average Mohs hardness of 8. I'm using an emery grade mix specifically in this experiment. Again, you can get it from sanding paper, sanding cloth. Be careful to choose aluminium oxide, not silicon carbide varieties. Grinding discs, masonry grinding discs, which don't have any steel. It's just aluminium oxide glued together with a fiber mesh to hold it together. You don't need steel to do this. This is one of the big myths. But again, choose aluminium oxide instead of silicon carbide. Pure corundum is 9. Pure silicon carbide is 9.5, and diamond is the top of the scale at 10. Diamond dust is used to polish diamonds. You can use whatever I can use corundum to work corundum. I can use diamond to work diamond. So that's again one of these myths that they lost high technology people are ever so careful to muddy the waters with false information and pseudoscience. Some emery is a mixture of corundum and other substances, and the mixture is less abrasive with an average of 8. That's what I'm using. There we see the mix. Now it's important because some corundum for abrasives is commercially mined in Zimbabwe, Pakistan, Afghanistan, Russia, Sri Lanka and India. You can find it here in Australia, you can find it in Egypt, you can find it really spread across the world. There was actually a trade in this in ancient times, but emery grade corundum is found on the Greek island of Naxos. That's an important feature. Pliny talks about, well, he's specifically talking about cutting marble here, but he also talks about porphyry. The method is exactly the same. I'm cutting granite with this, but an important reference is this division, though apparently affected by the aid of iron or steel, is in reality affected by the sand only acting only by pressing upon the sand within a very fine cleft in the stone as it is moved to and fro. Exactly what you're seeing here. This is a masonry disc made out of steel, but on the edge there is diamond is embedded into it. The steel does not cut, the diamond does the cutting. Big steel circular saws or masonry drills are only as effective as the abrasive that's attached to them. So whether you're using steel or copper or bone, they push the sand, the abrasive, against the granite. That's how the cutting action is done. It's actually a grinding action, not a cutting action. Masonry drills, perfect example. They got that colored tip on them. Once that wears out, the tool is effectively useless. Steel is not some super weapon against granite.
Right, so I'm in a reasonable distance so far, and there we have the grinding down. So now that copper has split, so we've gone what is it, just over a mil thick, and because it gets hammered at the end, it would be a little bit lessened by that, but roughly the same. So we're losing more granite is being cut than what we are losing in the copper. So we have not ideal, but it is, yeah, so less copper is being lost compared to the amount of granite that we're cutting into.
There's quite a bit to consider. So Pliny Natural History actually talks a lot about important things, but again, it's not the iron that cuts, it's the sand, the act of pressing upon the sand. That's the only reason for the iron or the copper or the wood or the bone. That's how the action is. It's exactly what I'm doing now. So steel cutting blades, It's not the steel, it's the abrasive that cuts. And technically speaking, they're not really cutting. What they're doing is grinding away. And that's why there's that trench, that cleft has been cut into the stone. So a circular saw grinds away using the abrasive. So whatever the material is, it's insignificant. It's the abrasive that does the cutting. Still now and in the past, the only advantage is now we have high speed power to spin the blade or move the blade back and forth. That's the only difference. It's only got faster, but the principle has never been unchanged. On an angle grinder, you attach this. All it is aluminium oxide with a mesh background. There's no steel there. You could cut granite just by rolling up a piece of sandpaper and moving it back and forth. That is still the process now. Masonry drills, again, the same thing. It's not the steel, it's the abrasive, the tip, which cuts. Once that's gone, it's, there's no grinding action anymore. So I'll try to remember to link these videos, but you can use a bone and sand and water to cut hard stone. You can use a copper saw to cut hard stone. You could use steel too, you could use wood. It's the abrasive that cuts, it is not the steel, it is not even the copper, it's the abrasive that cuts. That's the same in the past and the same as is now.
Okay, so there's my saw blade, and we began with a straight edge, and now we're seeing it's becoming curved, and to leave the imprint of what would be thought of as to be a massive circular saw, but can be achieved with beginning with a copper blade and a straight edge. And as it gets worn down, because the pressure sort of is at the front and at the nose, and now as we move out, we can see that the groove it's created is, of course, going to be just the nature of the way things work, is shallow at one end, gets quite deep in the middle, and then becomes shallow at the end. From a straight, beginning with a straight blade and a straight action, the middle of the cut is always going to get the most cutting action, and it's going to rise up at the end, low in the middle, and high at the end. So this straight action, beginning with a straight blade, will create a curve.
Another thing that's really important about Pliny, he talks about the trade in statues and columns and so forth in other parts, but in regards to the abrasive or sand, so the sand of Ethiopia is the most highly esteemed for this purpose. To add to the trouble is entailed, we have to send to Ethiopia to get this stone. Now he's talking about marble, but in other parts he talks about porphyry, this very, very hard granite. And as far as India even, so to Ethiopia and India they were importing sand. These are the same, especially Indian is still where corundum mines, the abrasive mines still are now. Afghanistan as well. Indian sand is held in the next highest degree of estimation after the Ethiopian sand. It's better, second best in the, now it goes on a little bit further, but Indian sand should be calcined, so that means burnt. It's the best way to use it. The sand of Naxos has the same defect. Also that is Coptos, generally known as Egyptian sand. He also mentions for polishing marble statues, and this would apply just equally well for granite, also for cutting and giving a polish to precious stones, very hard stones. The preference was long given to the sand of Naxos. I will come to that in a moment, because the Isle of Cyprus, that's still where emery grade corundum is mined. More recently, however, stones imported from Armenia for this purpose have displaced those of Armenian abrasives. Again, even the Wikipedia article, emery grade corundum is found on the Greek island of Naxos. But the trade for this goes far. Now he's talking about cutting marble. However, evidence for the use of corundum as abrasive in Egypt, this is something that the lost high technology, precise, advanced machinery people won't tell you. It's just so many of the things. Never let the truth get in the way of a good story. That's the fundamental principle of it. So later cultures, porphyry, this ultra hard, which was beautifully polished. Again, this is another example, giant box with right angles and smooth finish, and also Roman basalt. All this is carefully hidden by the lost high ancient technology, precision, advanced machinery, deception, scam is what it is. The last 10 times speed piece I just showed, well, this is it in real time, and I think because it's just worth explaining the process. So having created that wall around it, which I could have used clay, but just to be less messy, I used poster putty or blue tack as we call it. I began by putting in some of the emery grade abrasive, then I put the water in there. The water is an important part, so those striations that can be found on the copper cores, but also those cuts, it's very important to be that it's lubricated with oil or water, as studies have shown. There's important information there I'll get back to in regards to the sophistry of this precision machining lost high technology crowd. But I just want to show the actual speed and the way I held the tool itself. Occasionally I went two-handed because I was getting a little bit tired or whatever. 90% or more of the time I'm operating the saw like this. I have my hand towards the back. This is one of the reasons why I didn't replicate the speed of other experiments, such as by Alexander Sokolov channel and the Scientists Against Smith channel. They were getting a higher production rate, but they were holding their saw in the middle. I was holding my saw at the back, so there was effectively no pressure or weight bearing down on the blade. I was just moving it back and forth. Now in my next attempts I'm going to change this, and I'm going to increase my speed of grinding or cutting into granite with a copper saw, and I'll do that with black granite especially. But just to highlight, so that's the speed if I was working faster. Also if I was working with a weight, or that I held the saw in the middle and I was pushing down on them more, this would increase also the rate of production. Mine is slower than other experiments that have been done.
Okay, we can, on a side note in regards to this, so that's a copper saw. This is a piece of granite. I used this saw to cut. Now the reason I stopped at this point is because I wanted to measure and test something. So the saw blade itself is, I just got a piece of copper pipe, 1.22 millimeter the thickness. So, and then I just took this pipe, I cut a piece and I hammered it down into a flat blade. Now the reason I wanted to do, well, it was convenient, but also wanted to do a test because it's going to show up on the camera. The blade has started to split, and it's split on the other side, and it probably won't show up, but it's very clear from here to here. But now very faint trace, there's just a hint of copper left in the middle. So now we can measure that and compare how much copper has been lost in regards to how much granite has been removed. So firstly, it's shallow at the end, so it's deep. So the cut itself is shaped more like that. It's not cut in that way, and the straight blade, which was originally straight, has worn down to basically match that shape. So that's why these circular saw marks are actually, well, it can be explained with primitive ancient technology and just the way that things work. So that's the blade's curve. But So if we measure the cut itself now, basically it's 23 centimeters touch over, but because of the shape of it, it's not consistent throughout. So I'm going to reduce that and let's put it down to 16 centimeters. And so that way we can now, I'm removing this part and that part so we can measure it in a cubic sense. So I'm being conservative in that sense, so 16 centimeters. The width of the cut is I'd say so 160 millimeters long by 5 millimeters, and the depth, which probably won't show up, but it's closer to 12, but let's go conservative and say 11 millimeters. So now we can work out the cubic of how much granite has been removed. Since we know the thickness of the blade of copper, and so then there you can see that it is not straight, how it's obviously being curved, but from there we can work out the amount of area that has been lost. I'm better off scratching that than drawing it. Okay, so that's 6 mil. So if that's the curved blade, there we have 6 millimeters. So if we just carry that through, now we know because it's just a hammered blade, so if the blade was in profile, that's 2.44 millimeters, and I'll just make it easy. The length of the blade is 39. Let's just call that. Let's just call it what it is. 39 millimeters in length. So then we, basically form a triangle. We know the width of the blade, the length, and so now won't do that on camera, but I'll go off. So what we now can work out is how much granite, cubic volume in millimeters, has been removed, and how much copper has been lost in regards to that. So I'll take that off. I'll just run the numbers, and it's it's even just by looking at it, it's quite obvious we lose a lot more granite than what we lose in copper.
Now we can get an estimate of how much granite is lost in relation to the copper. So that's a concave, so it's a curved shape. So to turn it into a cubic, I've adjusted for the fact that it's very deep in the middle as it is compared to the end. So I reduced the length of the cut to 16 centimeters or 160 millimeters. So again, so that's the shape of the cut, and I've cut that down to take into account the fact that it's not a perfectly straight line. So I've adjusted this to take account of the concave shape. The amount of granite removed is no less than 8,800 cubic millimeters of granite. So how much copper is lost? Because now the blade, which was straight, has now become curved. But because I used, it's a very bad illustration, but because it was a flattened copper piece, we know the thickness of the copper, and so at that point we know how much copper is lost. And I have not, the blade is curved, but I've just used a simple triangle to work that out. So that would be basically double the triangle. So that triangle would go on the other side. But so how much copper is lost? This would be 39, the full length, times 6 millimeters times 2.44 millimeters, the thickness of the blade in itself. So this is an overestimate, and we have 570.96 millimeters of copper has been lost, and that's overestimated. I haven't taken into account that the curve would trim off a little bit, so that's an overestimate of the amount of copper lost. And so at the very, very least is a 15.4 to 1 ratio. So every 15.4 cubic millimeters of of granite that's removed, you lose 1 cubic millimeter of copper. So again, using this abrasive method, even though the copper is not as hard on most scales, they say, well, unlike the granite, which is very firm, very strong, the copper is malleable, and so it gets embedded with abrasive, and that actually forms a coating which prevents the further loss of copper. So every 15.4 cubic millimeters, centimeters, feet, however you want to measure it, you only lose 1 in copper. So the ratio of granite to copper is quite in copper's favor. So again, you might have heard, oh, but you know, these experiments and you lose so much copper. Well, actually you don't lose that much copper in respect to the amount of granite that's lost, but also if you save the slurry, so the material which is coming out is now relatively copper rich, so you could, by saving that material, putting it back in the furnace, you'd actually lose a tiny amount of copper because you can recapture that copper back quite easily as well. And copper is, you know, copper coins was still probably in some places is money. Copper is money. People strip homes for the wiring and the piping because copper has value, and in the past it was even more valuable than what it is now. So yeah, so firstly, in the actual process, the amount of granite to copper is much higher granite is lost, but even the copper that's worn down is not lost because it becomes part of the slurry of the abrasive that you're applying it, so you'll be able to recapture most of that very easily. Okay, so I've used some stone hammers just to bring those edges in closer. And definitely be worth an examination all on its own, but to cut in closer to the edge of a copper saw blade, instead of using a steel chisel, I just had a bit of fun and mucked around with a stone hammer. It was just a river pebble that I picked up from front garden. It's actually a very effective tool for different. Now, I would prefer steel chisels or steel tools for some jobs, but experimenting more and more, I realised, well, firstly, these things are easy. So instead of all the work that goes into creating the steel or other metals, these are you just pick one up and you just work at it, and when it's no longer useful, you throw it away and pick up another one. They're very cheap, they're very easy, and they're very effective. And also has parts broke off from the hammer. I got these little shards which were like a napped piece of flint, and they were razor blades as well. So there's cool little tools that just happen to be made along the way as well. So this deserves much more exploration, but when again the precision machining, advanced, ancient, lost high technology machinery, they poo-poo abrasives, they poo-poo stone tools and they poo-poo copper. And well, that's just so important to their narrative, to poison the well against these very effective, proven now. It's not just theory of, if you do the and these are things you can do for yourself, and you work at these and you'll realize just how good these tools are and just how wrong and deceptive the advanced precision, ancient, lost high technology machinery people are in regards to the things they say are impossible or fact, or the time scales they give for it. It's just all wrong. Please, please, please just try this for yourself. The next part of the experiment was to use that saw cut that I'd made with a copper saw into granite. Very thin cut, I might add as well. I'll even show you an even thinner cut later. But then I wanted to use copper and timber in similar, essentially the plug and feather technique. So these shims I just insert into the groove, and then I use, Americans will call them popsicle sticks, lolly sticks, we call them paddle pop sticks. So I just insert the copper, and then I just get thin pieces of wood, insert those in there and hammer those down, and then I wet the wood so the wood would expand and eventually force this cut. Now I'm going to insert a piece of video at this point. I think it's a very important one in regards to splitting granite.
Actually happened to us, where we had to use little shims to make up for it. Also, underneath that big stone there, you can see the shims, except it's not carved fancy. But I'm going to do a little carving demonstration. I'm going to prove that you don't need iron tools to do this. Now, this is my brother Jeff, and he actually sells granite stones. And he's going to talk a little bit about them. Just explain it. What kind of granite is this, Jeffrey?
Well, this is that rose-colored granite, and it's the same stuff that they used in Egypt in a lot of the projects out there. When they used granite, this is just a regular basic granite, tombstone granite, but these are Belgian block, and obviously they come from different areas. And it depends what minerals are in them. I mean, this granite here is like a, granite that they stuck in the old farmhouses and everything. This is very hard to work with. Matter of fact, this came off my property, and I've never seen stone so hard as this.
Could this stone be shaped with another stone, no problem?
Yeah, I mean, as long as you have a harder stone and you beat on it long enough, you can. One thing about granite, it's very predictable if you want to snap it.
Right.
These types of granites you can snap anywhere you want. If you score them and snap them, they'll snap perfect. This one here, not so much. Depends what minerals are in it.
Okay, and once I get it down and I want to polish it, what would I do ancient way?
Well, you just take a flat stone, very flat stone, and you would put water on there and sand. Water and sand, and back and forth and around. And it would take that right down and give that like a honed finish, almost like a polished finish. Matter of fact, years ago when I put my countertops in, I did them by hand with sandpaper. I did all the edges by hand, and they come out just as beautiful as the top. Can certainly be done.
To split my stone using that groove I cut into granite with a copper saw, I just used some copper. Again, I just inserted lollipop sticks, paddle pop sticks, popsicle sticks as pending, and then eventually just hammered those down with, well, I could have used any hammer. I used a stone just to stay in character. Then I apply water to make the timber expand, to push the crack open. And so if for instance you put them in, as in the past they would use wooden wedges, you place those in, you wet them up, you let them expand, you leave them there. But you also can take advantage, for instance, in the Egyptian quarries, such as Mons Claudianus or Aswan, where you take advantage of the heat of the day and the cool of the night. In the desert, it gets very cold at night and it gets very hot during the day. So unfortunately I didn't get it. Well, this is no mystery to split granite, just as we saw actual people who know their stone talk about it. Granite wants to be split along these types of lines, but I didn't quite capture it on camera. But that's, well, if you want to argue that point, but this is just a well-known fact anyway. So that's the process by which I used to split the granite, because I wanted to reveal how that cut with the straight copper blade, which became a curved copper blade, and the striations that are left behind, which of course perfectly replicate the so-called ancient precision advanced powered circular saw marks that are impossible to do with Stone Age technology, yet I done it. Okay, and so now the unveiling, using nothing but primitive technology, stone tools and copper to work this granite. What do we have? We have a circular saw, giant circular saw mark, including the striations, which was actually created with a copper blade that began as a straight edge, but just by working that particular action, we worked it down into a curved blade, and using the abrasive, lubricated, as is described in all these reproductions and also all these papers which are suppressed. When these papers are mentioned, they actually cut out, they don't show you the important sections of them, which is another part of this deception. This was not created by some giant advanced circular saw spinning at high rotations. They will tell you that those striations can only be achieved. This is Christopher Dunn, Brien Foerster, UnchartedX, all these other channels will tell you these striations can only be achieved by a high-speed tool. Absolutely untrue. You can do this and test this for yourself. I've just shown you how. Many more experiments to come. But now, just as they do, if you put water on the surface, the striations, those apparent marks which can only be achieved by advanced machinery moving at a high rate, they will literally say it's impossible to do with primitive techniques. They literally tell you that there have been no experiments, that the mainstream cannot describe it. Yes, they can. Yes, they have. And I've just proven it to myself, and I'm proving it to you now. It can be done. And those striations exactly match those which are said to be impossible with copper tools. The thickness of the cut, actually the thinness of the cut, is thinner than what they say is impossible to achieve. I'll actually show you another section at the end of this where I took that blade which had split in two and I reduced it to a 1.2 millimeter blade, and then I do the same cut again into granite as well. That's just anyway, I'll show you that in a moment. Those striations, that circular saw profile, all of this can be, has been, right here, has been achieved with ancient primitive techniques known to exist. And well, there you are. There's nothing more to be said about it. They can use all the mental gymnastics they want. They can try and cover things up all they want. But the fact is, it has been done. It can be done. It can be done. And I've done it right here.
Wow.
This particular channel and these videos, so UnchartedX, evidence for ancient high technology part 1 machining, part 2, as well as also his scientific study of core hole drilling, basically a case study in pseudoscience, tricky marketing, and just deception and censorship because of the deletion of comments that are even civil yet critical of his argument. But here's the video, there's the time code. The very thin width of the blade, as indicated by the thin lip at the edge of this cut, makes it nothing short of impossible that such a saw could have been made by a soft material like copper or bronze and still manage to cut through basalt. Well, firstly, that still managed to cut through basalt. It's not the steel, it's not the copper, it's not the bone, or it's not the paper in sandpaper that does the cutting, it's the abrasive. This is true with modern equipment, and this is true with primitive ancient technology. So no, it is not true at all that soft copper or bronze could not do this. I've just demonstrated that. But he says the very thin, the very tiny width of the blade as indicated by the lip at the edge of this cut makes it nothing short of impossible that such a saw could have been made by soft material like copper and bronze. So here's some other images from that same video. There we see the lip. That's the same stone, and there we see the angle with a finger as to give a sense of scale. Well, with my primitive copper hand tool, I got a 5 millimeter thick cut. However, that blade was a flattened piece of copper tubing which had a wall thickness of 1.2 millimeters. Once this had been ground through, my second experiment, as I'll show you now, was I bent the blade to one side, leaving a 1.2 millimeter copper blade, and I managed to effect a cut as well.
Wow!
Everything, literally everything described as impossible by the lost high ancient technology, precision advanced machinery of the ancient times industry is actually possible with primitive tools. The only invalid argument to be made in their favor is that historic techniques are slower than modern power tools. Well, welcome to history. People once spent months or years migrating to new locations instead of flying that distance in a few short hours. They would have to walk across continents or sail across oceans, months or years to do what we now do in hours or at most 24 hours. People used to have to hand milk cows, then churn that milk into butter instead of just dashing down to the supermarket in a few minutes. Before the industrial age and modern power tools, stone workers, people working with stone, would have to patiently work at it. If you wanted to cut a stone, you would have to do it with primitive techniques using abrasive and a blade. So whether it was copper, whether it was bone, whether it was steel, it just took time to do. This was the nature of the world. People before planes, trains and automobiles, people used to have to walk or ride horses. They would have to sail across oceans. Welcome to history. Things took time. So, impossible without a giant high-speed circular saw. The verdict is bunk. If the lost high ancient technology, precision advanced machining crowd spent a little bit of time actually doing experiments rather than just pointing at stones and charging people thousands of dollars for it, they would find that it is not impossible. But of course, they rely on censorship and deception to promote their cause. So, success with only sand and copper. Of course, this will be censored, comments will be deleted, hidden, people will be blocked, but that's how they operate because it's an industry built on lies. Now, let's anticipate some of the mental gymnastics, but also it would be a legitimate question. So that original copper blade, which was a folded tube with a thickness of 2.4 mil, I've now just folded that over, so the blade is now even thinner. The blade is 1.22 millimeters in diameter. Using exactly the same technique which I did the cut previously, I've created that same cut. Once we remove the guide stone, I could just follow the groove. Now I didn't have to go all the way through, because once we start the cut we can just carry it through. But the important question is how to create that very deep cut. Well, firstly, again, that's 2 millimeters, maybe a touch over 2 millimeters thickness of that groove. Supposedly impossible with soft tools. But the question is, with this type of technique, it's good up to an inch or two of the thickness of a blade. So how do we cut even further? How do we make those very deep cuts? Well, with that shallow trench there, I've cut it close to the edge because I want to trim that off. And then with a hammer, with a stone hammer, I go along and I can knock that edge off very easily. So now instead of, now I'm open to cut even more. The blade that I've used there is mounted in the center. All I need to do is have a side mounted blade using the exact same technique, just having the blade mounted on the side. I wrap it around the piece of wood rather than have it attached in the center, and I can go as deep as I want. You can go as deep as you want. You can literally do this with stuff around the house. You might need a few pieces from the hardware store, but most of it you will already find in your home, and you'll be able to make these very, very easily. So everything that the lost high technology, advanced precision machining describe as impossible is possible. And it's just a matter of doing the experimentation and proving beyond a doubt that the impossible is actually possible.
It's time to